The rational root theorem is the last thing that we need in order to be able to factor all polynomial functions that have rational roots. So all factorable polynomial functions. And it states the following. So given this polynomial function, so an arbitrary polynomial function, all rational roots of the function are of the form p over q, where p is a factor of the constant term. So the constant term would be this one, the a0, constant, and q is a factor of the leading coefficient. So this would be our leading coefficient. So a1. So this allows us to list all the possible rational roots of a function. So we would start by listing the factors. In this one, negative 30 is our constant term, and 2 is our leading coefficients. So p are the factors of the constant term. So for p, we're going to list all the numbers that multiply, that possibly could multiply to negative 30. And for each of these, we have to remember that there's a plus or a minus. So plus or minus 1, plus or minus 2, plus or minus 3, not 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. Those are just all of the factors of the constant term. And then q is all the factors of the leading coefficient. So our leading coefficient is 2, so plus or minus 1 and plus or minus 2. So now we have to list all the possible combinations of p over q. So we could have any of these factors divided by 1, so all the possibilities, and we only have to account for the plus or minus 1 time. So really it's going to be this list, so because this would be all of them divided by 1, so let's just write them out all again. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. And then we will go through and list all of these, but also divided by 2. But notice we're going to get some that are repeats, so we don't have to list them again. So plus or minus a half, because that's 1 over 2. But if we list 2 over 2, we'll write it anyway, but notice that that's just going to equal 1. But then these other ones, six over 2 is another one that divides to 3. And 10 over 2 divides to 5. And plus or minus 30 over 2 will divide to 15. So I'm going to cross out all of my repeated ones. So 30 over 2 is a repeat, 10 over 2 is a repeat, 6 over 2 is a repeat, and 2 over 2 is a repeat. So this is an exhaustive list. So these are all of the numbers that could possibly be a rational root of this function. Now luckily you have a nice algebra teacher, so when I ask you to factor things, they won't have this long a list of possible rational roots. So here, let's use the rational root theorem and synthetic division, and then we can completely factor a polynomial. So what that looks like is, first we'll list out the possible rational roots. Notice that here we have a 1, so that actually saves us a lot of time. We only have one set of factors to list out. So the possible rational roots are the factors of 6, which would be 1, 2, 3, and 6. And then what we do is we're going to use synthetic division to see if any of these evenly divide our function. So let's first test -1. So I'm testing if x minus 1 is a factor. And to do that, I'm going to divide my function by x minus 1. And I can do that with synthetic division. So 1, -4, 1, and 6. Drop the 1 down. 1 times 1 is 1. -3. 1 plus -3 is -2. -2 times 1 is -2. And I got a remainder. So because I got a remainder, because the remainder is non-zero, x minus 1 is not a factor. So then we have to just go down the list until we get one that is a factor. Like I said, I'm a nice person, so I usually will not make you test more than 1 or 2 or 3 maybe, depending on what order you're testing them. So now let's test if x plus 1 is a factor. And to do that, we divide by x plus 1. At this point also, if you're still using long division for all of your polynomial division needs, you can see how this would get extremely tedious using long division. -5 plus times -1 is 5. 6. 6 times -1 is -6. And we did in fact get a 0 remainder. So x plus 1 is a factor, which means that x cubed, our original function, x cubed minus 4x squared plus x plus 6 equals x plus 1 times x squared minus 5x plus 6. And then we don't have to use synthetic division again because we've reduced it to a factorable quadratic. X squared minus 5x plus 6 is going to factor into x minus 2 times x minus 3. So we only had to use the synthetic division method once. It's minus 2 x minus 3. And we can do a check here. X minus 2 is one of our possible roots, and x minus 3 is also one of our possible roots. So this would mean the roots of this function are -1, +2, and +3. So the last thing is sometimes we get zeros that are complex. And when we get complex zeros, they always occur in complex conjugate pairs. So if a plus bi is a 0 of the function, then the conjugate a minus bi is also a 0 of the function. So find all zeros of h of x equals x cubed plus 2x squared minus 38x plus 80, given that x equals 3 minus I is a root. So if x minus 3i is a root, then x plus 3i, or x equals, so x equals 3 minus I is a root, then that also means x equals 3 plus I is a root. So we know two of the factors are, in fact, x minus 3 minus I is a factor, and x minus 3 plus I is a factor. If we multiply these two factors together, we will get a quadratic function that will evenly divide our original function, and we can find what our last factor is. Now, multiplying these together looks like it's going to be bad, but with some clever rearranging, we can actually make this work out nicely. So x minus 3 minus I, I'm going to distribute this negative. And then I have x minus 3 plus I. And I'm going to do the same thing here. X minus 3 minus I. Now, I'm going to add another set of parentheses. Right here. I'm going to put my x minus 3's in parentheses. This is a hidden example of difference of squares. Remember how I said that formula just keeps on helping you out? In this difference of squares, this is, so x minus 3 is a, so we have a plus b, our b is I, and then here we have the same thing, minus b. So usually we've used this for factoring. Now we're actually going to use it for multiplying, because we know that a plus b times a minus b always and forever multiplies to a squared minus b squared. And try it for yourself if you don't believe me. A squared minus ab plus ab minus b squared. So why does that help us? Well, it saves us the trouble of doing multiplication with a 3 terms by another 3 terms. We know that this is going to be x minus 3 squared minus I squared. And it gets rid of all that annoying complex number multiplying. The only thing we have to remember is that I squared equals negative 1. And we know x minus 3 squared is x squared minus 6x plus 9. I squared is negative 1, so it's minus negative 1, which then leaves us with x squared minus 6x plus 10. So now this is a quadratic function that has these two roots. If you use the quadratic formula on this function, you'll get these two as your answer. But now the point of that is, now that we have a quadratic function, we can use long division. We're going to divide that new function, x squared minus 6x plus 10. And our original function of x cubed plus 2x squared minus 38x plus 80. So the we should get a linear term as our answer, or a linear binomial as our answer, and that will tell us what the last factor of this equation is. So x squared times x would give me x cubed minus 6x squared plus 10x. So subtracting gives us 0. 2x squared minus negative 6x squared gives us 8x squared. Negative 38x minus negative 10x, or minus 10x gives us minus 48x. And then we drop the 80 down. So then I need to multiply x squared by positive 8 to get my 8x squared to cancel out. And I'm left with 8x squared minus 48x plus 80. And when I subtract all of that, everything goes to 0, so no remainder. And this is my final linear factor. So the three zeros of this function are x equals 3 plus or minus I, and x equals negative 8. And writing the function as a product of linear factors would be x minus 3 plus I, x minus 3 minus I, and x plus 8.